session 5, we are going to study that self-purification and what will happen to the pollutant and what will happen to the quality of the river when it is disposed of, when sewage is disposed of to a nearby to a stream. See, on the first thing we have to understand here in a river stream is oxygen sac curve. What is this oxygen sac curve? The oxygen sac, or it's also called as oxygen deficit in the stream at any point of time during self-purification process. So you have to understand this. We are dealing with self-purification of process. It is the difference between saturation DO content of the river and the actual DO content at that time. The amount of resultant oxygen deficit can be obtained by algebraically adding the de-oxygenation and re-oxygenation curves. So oxygen deficit D can be calculated by saturation DO minus actual DO. So whatever the resultant curve you are going to obtain is called oxygen sag curve. Why sag is? It is in the sag formation, so we call it as sag. So what you have to understand is, in a river, understand, the difference between the saturation DO. See, saturation DO of a water, it varies from around 14 milligram per liter at about temperature 0 degrees Celsius to 7 or 8 at 30 milligram per liter. And the DO depends upon the temperature, understand. So the saturation DO will be around 14 at the 0 degree and will be around some 7 when the temperature is 30 degree Celsius. So you never get this saturation DO in the river. Okay. What you get is only the actual DO. So whatever the DO you are going to measure at a particular point at a particular time, understand, if you detect that by the saturation DO, you get the oxygen deficit. That is the deficit that is needed at that particular point and time. That's called oxygen deficit. Once we see the graph, you're going to understand this. See here, this is a curve showing de-oxygenation, re-oxygenation, and oxygenation curve. Again, I am telling you, whatever we have discussed in the session 4 about self-purification of stream that will take place by physical forces and chemical forces, we are understanding that here. See, initially we have got an time of flow in streams in T days in the x-axis. In the y content or the y-axis is DO content in percentage. See here, this is the point of oxygen demanding the waste discharge. An arrow mark you can see here. At this point we have discharged the waste to a river. Riverಗೆ ಇಲ್ಲಿ ನಾವು ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ವೇಸ್ಟ್ ನ ಹಾಕಿದೀವಿ. So at that particular point, oxygen which is present at that point is some value, understand. Saturation DO is the line you are seeing at the top of the line. Okay, it depends upon the temperature, as I said. So that is the saturation DO, and the point where you got the curve is starting, that is the point where the oxygen level at that particular point. So the difference DO is nothing but that is the deficit. So that is the difference between saturation DO and the DO at that point. Okay. So as the river is moving, even the waste is also moving. So the degradation starts. As you can remember, zone of degradation, the degradation starts. So when the degradation starts, the microorganisms which are present in the sewage consumes the dissolved oxygen present in the river. So when the dissolved oxygen is consumed in of the river is consumed by the microorganisms, the DO level starts coming down. So the dissolved oxygen which is present at the initial point is going down. That means the deficit is increasing, the difference is increasing. So at any point T on the curve, the oxygen deficit is represented by dt. So that And as the river moves, we move on to zone of active degradation, where the activity will be very high. All microorganisms are going to convert the pollutants which are present in the sewage. So it requires a lot of dissolved oxygen. Oxygen level comes down. Okay, so the DO level drops down to 1 or less than 1 milligram per liter. So you can see the graph. So DO is there, DT is there, and again it is going down. And DC is the deficit. Means at this critical point, oxygen level is very low. At that critical point, maybe 0 to 1 milligram per liter. So the deficit increases. And that means the requirement of the oxygen at that particular point is increasing. So in the zone of recovery, see at that point, critical point, most of the pollutants have been stabilized into final products. So there is the pollutant concentration has come down. So there is a recovery, means oxygen, the dissolved oxygen level in the river is increasing. So the deficit is also going down, and it has come down to this point where the oxygen deficit is very less. So this is called oxygen sac curve. Why they call it a sac curve? Initially oxygen is high, DO, and the degradation starts. The dissolved oxygen level coming down. At particular point, it's the maximum. It's the lowest oxygen level. Then river has got the ability, as we said. So oxygen level in the river is coming up, and it has taken this shape. So this is called oxygen sac curve. So I'm dealing with only dissolved oxygen about this point, but you can see there are other two curves. Initially, you can see you just see the deoxygenation curve. It has started with this initial point where you have got the DO. So as the DO is consuming and the microorganisms, the deoxygenation curve is also going down. Okay, so the microorganisms has consumed all the oxygen which are present in this one. So that is shown by the deoxygenation curve. But nature has got its own ability. Understand, it is going to put the oxygen to the river. It is not going to make it zero because of splashing of water waves and because of the algal activities. So the oxygen is going to be added up into the river through these natural agencies. So re-oxygenation, initially at the point of zero, we were not required re-oxygenation. But as you put the waste discharge at this point, the deoxygenation starts, means the nature also starts re-oxygenation. ಇಲ್ಲಿ ನೋಡಿ, so re-oxygenation ಹೀಗೆ increase ಆಗ್ತಾ ಹೋಗ್ತಾ ಇದೆ. When the re-oxygenation is max, so you have got the oxygen sac curve also very good, means the deficit is also very less. So whenever a waste is thrown into a nearby river, that is the effluent, understand, deoxygenation, the degradation of the waste takes place, and when it takes place, oxygen level in the water comes down. So that is shown by the deoxygenation curve. But nature has is going to put the oxygen in the form of air to the water and through algae. So reoxygenation takes place. So this activity is a continuous process, deoxygenation, reoxygenation. So because of this, you have got a DO profile, understand, that's called oxygen sac curve. So it happens continuously in any stream whenever a waste is thrown. So we are going to understand this mathematically in this session 5. Again, whatever I have discussed here, it has been written here, deoxygenation and reoxygenation curve. Let's see what is deoxygenation curve. The curve which represents or showing the depletion of DO with time at the given temperature is called deoxygenation curve, which shows the depletion of DO. I'll go back to the, the previous slide. See here, deoxygenation. ಇಲ್ಲಿ ಇನಿಷಿಯಲ್ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಡಿಆಕ್ಸಿನೇಷನ್ ಏನು ಸುಮ್ಮನೆ ಎಷ್ಟಿತ್ತು ಅಷ್ಟಿತ್ತು, ಅಲ್ಲಿಂದ DO ಲೆವೆಲ್ ಕಮ್ಮಿ ಆಗ್ತಾ ಬರ್ತಾ ಇದೆ. ಹಾಗಾಗಿ ಆಕ್ಸಿಜನ್ ಕನ್ಸಂಪ್ಷನ್ ಆಗ್ತಾ ಇದೆ, ಇಳಿತಾ ಹೋಗ್ತಾ ಇದೆ. ಡಿಆಕ್ಸಿಜನ್ ಬರೀ ಇದೊಂದೇ ಇದ್ದಿದ್ರೆ ಓನ್ಲಿ ದಿಸ್ ಕರ್ವ್ ವಿ ವುಡ್ ಹ್ಯಾವ್ ಗಾಟ್. ಬಟ್ the river has got a reoxygenation components also. So in the what you got is a oxygen sac. Coming to the reoxygenation, in order to counterbalance the consumption of dissolved oxygen due to the deoxygenation, atmosphere supplies oxygen to the water, and the process is called re-oxygenation. So, as I said, when the wastewater is discharged into the stream, the DO level in the stream goes on depleting. This depletion of DO content is known as deoxygenation, whatever I have explained in the above line. So, reoxygenation is to counterbalance the deoxygenation, which happens by the nature. And this is what I want to see here. A river is flowing with a velocity u. You are and we are throwing the effluent from the sewage treatment plant at x is equal to 0 and the time is 0. As the time is 0, then a river starts flowing in the flowing direction, and it mixes the wastewater which has been thrown to the river is going to mixed up with the water, and it is also moving. So at the initial point the oxygen was good, 6 to 7, for example I'm telling, 6 to 7 milligram per liter. But as and when you have thrown the waste to that one, understand, a lot of organics are present, maybe settleable and dissolved. So that acts as a food for microorganisms. The microorganism starts the degradation of that one. So at the point x is equal to 0, t0, the activity starts. So when the activity starts, the dissolved oxygen which was present at that point, here the curve is coming down. Okay, so the curve is coming down, dissolved oxygen is dipping down. So ಇದು ಹೀಗೆ ಇಳಿತಾ ಬರ್ತಾ ಇದೆ. Then as the river is moving, ನಾನು ಹೇಳಿದ್ನಲ್ಲ, zone of degradation, zone of active recovery, active degradation. So critical point is nothing but zone of active degradation, ಅಲ್ಲಿವರೆಗೂ ಬರ್ತಾ ಇದೆ. So river is moving, it's the pollutants or the whatever we have thrown, it is also moving with the river. So after this critical point, most of the pollutants have been stabilized into products, understand. So there is not much of a organic which is present here. So degradation, the rate comes down, that is deoxygenation rate comes down, reoxygenation rate goes up. So when the reoxygenation rate goes up, the amount of oxygen that is in the river starts climbing up or moving up in the direction. So reoxygenation rate ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗ್ತಾ ಇದೆ. So it is going up and ಬಂದು then saturation DO ತೋರಿಸಿದೀವಿ. Sometimes it may go to the saturation DO, sometimes it may not be, may be well below the saturation DO. ಸೊ ಎಷ್ಟೋ ದೂರ ಆದಮೇಲೆ ಎಲ್ಲಿ ಪೊಲ್ಯೂಷನ್ ನೀವು ಪೊಲ್ಯೂಟೆಂಟ್ನ ಥ್ರೋ ಮಾಡಿರ್ತೀರ ಅದಕ್ಕಿಂತ ಎಷ್ಟೋ ದೂರ ಹೋದ್ಮೇಲೆ ರಿಕವರಿ ಪೂರ್ತಿ ಆಗುತ್ತೆ. ಸೊ ಬೈ ದ ಟೈಮ್ ದೀಸ್ ಥಿಂಗ್ಸ್ ಹ್ಯಾಪನ್, zone of degradation, zone of active degradation, zone of recovery, and clear zone. So wherever you are going to throw the wastewater into a river, listen, this happens. So the DO which was gone down to a critical point has gone up because of self purification of stream. To understand this mathematically, Streeter Phelps has given an equation for this one. So this is whatever you are saying is Streeter Phelps oxygen sacker, and he has given equations for these. ಇನ್ನೊಂದ್ಸಲ ನೀಟಾಗಿ ನೋಡ್ಕೊಂಬಿಡಿ. ಪೊಲ್ಯೂಷನ್ ಟೈಮ್ 0 ಇದೆ, ಡಿಸ್ಟೆನ್ಸ್ ಎಕ್ಸ್, ಆ ಸ್ಪಾಟಲ್ಲಿ ನಾವು ಬಿಡ್ತಾ ಇದ್ದೀವಿ ಎಕ್ಸ್ 0. ಇದು 1 ಕಿಲೋಮೀಟರ್, 3 ಕಿಲೋಮೀಟರ್, 4 ಕಿಲೋಮೀಟರ್, 5 ಕಿಲೋಮೀಟರ್ಸ್ ಇಟ್ ಮೇ ಮೂವ್ ವಿತ್ ದ ರಿವರ್. So as and when it is moving, degradation is happening, and it is going to reach the critical point also, the river, the dissolved oxygen. Then reoxygenation rate increases, the oxygen level has gone up, ಮತ್ತೆ stabilize ಆಗಿದೆ, and river has become natural. So it by on its own, the river has degraded the pollutant which we have thrown. So whatever we have been discussing, DO deficit, DO saccharine, all these things, it is nothing but the difference between the DO saturation DO and the DO at that particular point. So you see, I am showing you a curve here. Location of phase discharge BOD at that point. ಅಲ್ಲಿ ಆ ಸ್ಪಾಟಲ್ಲಿ ನಾವು ಥ್ರೋ ಮಾಡಿದ್ದೀವಿ. At that particular point, oxygen level, dissolved oxygen level is C, and the saturation value is CS ಅಂತ ತಗೊಂಡಿದ್ದೀನಿ. That is, dissolved oxygen saturation level is CS, the horizontal line, and at this point, initial point where the curve is starting is C. So that CS minus C is nothing but dissolved oxygen concentration is not, I have taken it as D at any point of time. At the initial point at 0, I have taken it as D0. D0 ಅಂದ್ರೆ CS 0 ಇಂದ ಮೇಲ್ಗಡೆವರೆಗೂ ಮೆಜರ್ ಮಾಡ್ತಿರಲ್ಲ ಸ್ಯಾಚುರೇಷನ್ CS ಮೈನಸ್ ಸಿ ಅಂದ್ರೆ ಕೆಳಗಡೆಯಿಂದ ಪಾಯಿಂಟ್ ಸ್ಟಾರ್ಟಿಂಗ್ ಇದೆಯಲ್ಲ ಅಲ್ಲಿವರೆಗೂ ಮೆಜರ್ ಮಾಡ್ತೀವಲ್ಲ ಅದು, ದಟ್ ಈಸ್ ಡಿಸಾಲ್ವ್ಡ್ ಆಕ್ಸಿಜನ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ವಿಚ್ ಇಸ್ ಪ್ರೆಸೆಂಟ್ ಇನ್ ದ ಸ್ಟ್ರೀಮ್ at that point DO. ಹಾಗೆ ನೆಕ್ಸ್ಟ್ ಟೈಮ್ ಬಂದಾಗ ಸಿ ಅಂತಿದೆ ಕ್ರಿಟಿಕಲ್ ಪಾಯಿಂಟು, ಅಲ್ಲಿ CS ಮೈನಸ್ CC ಕೆಳಗಡೆಯಿಂದ ಮೆಜರ್ ಮಾಡ್ತೀವಲ್ಲ ಅದು CC, ಆ ಡಿಫರೆನ್ಸ್ DC ಆಗುತ್ತೆ. ಅಟ್ ಎನಿ ಪಾಯಿಂಟ್ ಆಫ್ ಟೈಮ್ ಡಿ ನೋಡಿ ಸಿ ಅಂತ ಕೊಟ್ಟಿದೆ ಇದ್ರ ಗ್ರೀನ್ ಲೈನ್ ಅಲ್ಲಿ. ಸಿ ಕೆಳಗಡೆಯಿಂದ ಮೆಜರ್ ಮಾಡ್ತಿರಲ್ಲ, ದಟ್ ಸಿ ಈಸ್ ದ ಡಿಸಾಲ್ವ್ಡ್ ಆಕ್ಸಿಜನ್ ಲೆವೆಲ್ ಅಟ್ ದಟ್ ಟೈಮ್. ವಾಟ್ ಇಸ್ ದ ಸ್ಯಾಚುರೇಷನ್? ಸ್ಯಾಚುರೇಷನ್ ಲೆವೆಲ್ ಫಾರ್ ಎ ಸ್ಟ್ರೀಮ್ ಇಸ್ ಆಲ್ವೇಸ್ ಸೇಮ್ ನಂಬರ್, ದಟ್ ಈಸ್ CS. ಸೊ CS ಇಂದ ಸಿ ಕಳೆದ್ರೆ ವಾಟ್ ಯು ಗೆಟ್ ಡಿಫಿಶಿಟ್ ಅಷ್ಟು ಇಲ್ಲ, ಅಷ್ಟು ಇರಬೇಕಾಯಿತು, ಅಷ್ಟು ಇಲ್ಲ. ರಿವರಲ್ಲಿ ಅಷ್ಟು ಡಿಫಿಶಿಟ್ ಹೊಡಿತಾ ಇದೆ ಅಂತ. ಇನಿಷಿಯಲ್ DO ಹೊಡಿತಾ ಇತ್ತು, ಯಾವಾಗಲೂ ರಿವರಲ್ಲಿ ಡಿಫಿಶಿಟ್ ಇರುತ್ತೆ. ನೋ ರಿವರ್ ಈಸ್ ಅಟ್ ದ ಸ್ಯಾಚುರೇಷನ್ ಲೆವೆಲ್ ಇರಲ್ಲ. ಹಾಗಾಗಿ ಮ್ಯಾಥಮೆಟಿಕಲ್ ನಾವು ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಆ ಸ್ಯಾಚುರೇಷನ್ ಲೆವೆಲ್ ಅನ್ನು ತಗೊಂಡು ಅಲ್ಲಿ ಬೇಸ್ಡ್ ಆನ್ ದ ಡಿಸಾಲ್ವ್ಡ್ ಆಕ್ಸಿಜನ್ ಅಟ್ ಎನಿ ಪಾಯಿಂಟ್ ಆಫ್ ಟೈಮ್ ಆನ್ ದ ರಿವರ್ ತಗೊಂಡು ಆ ಡಿಫ್ರೆನ್ಸ್ನ ನಾವು DO ಡಿಫಿಶಿಟ್ ಅಂತೀವಿ. ಸೊ ಏನೇ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಿದ್ರು DO ಡಿಫಿಶಿಟ್ ಅಲ್ಲಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ. ನೋಡಿ ಈ ಕರ್ವ್ ನೋಡ್ಕೊಳ್ಳಿ, ಆ್ಯಂಡ್ ಇಟ್ ಹಸ್ ಬೀನ್ ಗಿವನ್ ವೇರ್ D stands for dissolved oxygen deficit, that is the difference. CS is saturation concentration of dissolved oxygen. C, actual concentration of dissolved oxygen at any point. DO, initial deficit at the time 0. DC, critical DO deficit. CS, critical DO. CO, it is the dissolved oxygen concentration at 0. ಇದನ್ನೆಲ್ಲ ನೋಡ್ಕೊಂಡ್ಮೇಲೆ you get this curve, understand? ಇದನ್ನ what we are going to understand is, whenever ಇಲ್ಲಿ ನೋಡಿ ಕೆಳಗಡೆ, this is the point where you are throwing the waste water. ಮೇಲ್ಗಡೆಯಿಂದ QW, CW, LW, TW is the waste water which is coming and joining the river. That's that point, mixing of the wastewater takes place with the river. Mixing of wastewater with the river, dilution takes place. If large amount of water is there, it is very good for us. So dilution takes place at that point. ಈ ಮೇಲ್ಗಡೆ ಗ್ರಾಫ್ ಅಲ್ಲಿ ನೋಡೋದಾದ್ರೆ at T is equal to 0 ಸ್ಟಾರ್ಟಿಂಗ್ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಮಿಕ್ಸ್ ಆಗ್ತಾ ಇದೆ. Then zone of degradation starts. So now for my mathematical analysis, I have taken QR is volumetric flow rate, QW volumetric flow rate of wastewater, QM is mixing ಆದ್ಮೇಲೆ ಎರಡು ಮಿಕ್ಸ್ ಆಗೋದು QR QW, CR is dissolved oxygen concentration, CW dissolved oxygen concentration in the wastewater, TM is dissolved oxygen concentration in the mixing, TR temperature of the river, TW temperature of the wastewater, TM temperature of the river mixing. So wastewater is also there, river is also moving in this direction. You are going to mix up. You have to mix ಆದ್ಮೇಲೆ you get something else that is called mix. Okay, that is why ಎಲ್ಲಾನು represent ಮಾಡಿರೋದು M ಅಲ್ಲಿ. In the next slide, you will understand better. It's called mass balance. Mass balance plays a very important role. The brownish color is the wastewater which is coming here. The blue color is the river which is flowing, already flowing. both this brown and the blue, they are going to mix up the volume or the mass, understand, the increases, understand, and it has become Q naught, C naught, L naught, and QW is the discharge of wastewater, C is the dissolved oxygen, L is the BOD low, T is the temperature. And whereas for the river, it is QR, CR, LR, TR. Both are going to mix to form a Na, this one, Q naught, C naught, L naught. So, quite naturally, you know about the mass balance. You have studied in your earlier classes. Mass in is equal to mass out. So, for dissolved oxygen concentration ಏನಾಗುತ್ತೆ, it is C naught, that initial point, is equal to QW CW by plus QR CR by QW plus. So, mass in is equal to mass out. If you take, this is what you are going to get. C naught is equal to QW CW QR CR by QW plus QR. In the same way, see the BOD of the stream, the BOD of the wastewater, they are going to mix up to give a new BOD load. That is nothing but L naught. So L naught is again mass balance. We have found the value of L naught is QW LW plus QR L naught by QW plus QR. At the same time, the temperature of the wastewater is different, temperature of the river is different. When both are mixed up, you get a new temperature for the mix up, that's called TO. O andre outfall, that is a place where it is going to be mixed up. So T naught is QW TW plus QRTR by QW plus QR. This is the temperature. So by taking the mass balance, mass in is equal to mass out, we have found all these things. C naught, L naught, T naught. C naught is the initial dissolved oxygen concentration at the mixing point. You have to keep it in mind. Mixing ಆದ್ಮೇಲೆ ಸಿಗೋವಂಥದ್ದು C naught. ಇದು ಅಷ್ಟೇ L naught. ಯಾಕೆಂದರೆ ಹ್ಯೂಜ್ ಅಮೌಂಟ್ ಆಫ್ ವಾಟರ್ ಇರೋದ್ರಿಂದ ವೇಸ್ಟ್ ವಾಟರ್ ಎಷ್ಟೇ ಜಾಸ್ತಿ ಬಿಟ್ಟರುವೆ 500-600 ಮಿಲಿಗ್ರಾಮ್ ಪರ್ ಲೀಟರ್ ಬಿಟ್ಟರುವೆ ರಿವರ್ದು 3-4 ಮಿಲಿಗ್ರಾಮ್ ಪರ್ ಲೀಟರ್ ಇರುತ್ತೆ. ಎರಡು ಮಿಕ್ಸ್ ಆದಾಗ ಇಟ್ ವಿಲ್ ಕಮ್ ಡೌನ್. So L naught changes, T naught also changes. So this is the graph. For this, Streeter researcher, Streeter Phelps has given a model for this DO SAG equation. And you know, we have discussed this is how the SAG takes place in the river. Initial DO ಎಷ್ಟಿರುತ್ತೆ, degradation ಆದಾಗ ಪೂರ್ತಿ come down, it will go to a point max and again rises up. So he has given an equation. D is equal to KD into L naught into Ka minus Kd into e to the power minus Kd into e to the power minus Ka. So what you get is D dissolved oxygen deficit in the river is given by this equation. So we are using both de-oxygenation rate constant, re-aeration rate constant. As we have discussed in the previous class, whenever there is a de-oxygenation, the oxygen level coming down because of the bacterial activity, nature is also putting the air or the oxygen. So that's called re-aeration. So we have to take both re-aeration and de-oxygenation in the equation. So using that, dissolved oxygen deficit at any point of time on the curve is given by this equation. So Streeter Phelps has given this equation. Using this equation, you can find what is happening in the river. Whenever a wastewater is discharged, what will happen after 1 day, what is the DO concentration. See, there is no need to go to the river and find out what is the DO concentration after 1 day or at a distance of 4 kilometers from the point where we have put the wastewater into the river. There is no need to go and find out physically. Using this, definitely DO SAG equation given by Streeter and Phelps, you can find out this one. Because see, ಅಲ್ಲೇ ಕೊಟ್ಟಿದಾರಲ್ಲ, ಅಲ್ಲೇ ಕೊಟ್ಟಿರೋದ್ರಿಂದ see these things, you can find out this. See, de-oxygenation rate, you know, it happens in the river. De-oxygenation is nothing but consumption of this one. For that, what is the rate? At what rate it has happened? It is given by an empirical formula, and all these empirical formula holds good for 20 degrees Celsius, and we have to make the correction for the temperature where we are applying that this one, because temperature of the river won't be 20 degrees centigrade. It depends upon the places. So we make the temperature correction. And as far as re-aeration rate is also concerned, re-aeration rate also depends upon the temperature. Okay. And what is the time of traveled by the river? T is given by x by u. This also you can calculate. And time to the critical distance. So that is nothing but the distance, critical point idella, and what is the distance from the place we have thrown the wastewater. So what is the distance, at what distance we get the critical point or the lowest DO? These things can be calculated using these equations. Time to the critical distance. And what is the critical deficit? Critical deficit ಅಂದ್ರೆ lowest point, ಆಕ್ಸಿಜನ್ ಕರ್ವಲ್ಲಿ ಇರುತ್ತಲ್ಲ, ತುಂಬ ಕಮ್ಮಿ 1 milligram per liter ಇರುತ್ತಲ್ಲ, ಆಗ ಎಷ್ಟು ಡಿಫಿಷಿಟ್ ಇದೆ ಅಂತ ಕ್ಯಾಲ್ಕುಲೇಟೆಡ್. ಅದನ್ನ ಯೂಸಿಂಗ್ ಟ್ರೀ ಟು ಪೆಲ್ಪ್ಸ್ ವಿ ಗೆಟ್ ಡಿ ಸಿ ಇಸ್ ಈಕ್ವಲ್ ಟು KD L0 by Ka minus KD into e to the power minus KD TC. So KD is de-oxygenation rate constant, Ka is re-aeration. So deficit is the combination of Ka and KD. So what is the critical dissolved oxygen concentration, CC? CS minus DC, and critical distance x is equal to Tc into u. So what you have to understand, this Streeter-Phelps equation is going to give you the deficits, oxygen deficit in the stream. Okay, without doing any physical analysis, you can calculate all these things by mathematical and the formulas. So this is one way of disposal of wastewater, that is disposal of wastewater to a nearby river or a stream. That's called dilution. Another one is you can definitely dispose the treated wastewater to a nearby the field. Understand? So that we understand using sewage farming. Let's see what is sewage farming. The process in which sewage is used for growing crops is known as sewage farming. The process in which sewage is used for growing crops. So the fertilizing elements of sewage has got these types of fertilizing elements. Fertilizers, selenium, nitrates, sulfates, phosphates are all present in the sewage. So as it is present in the sewage, definitely sewage can be used for growing crops. So the nutrients of sewage make the fields fertile, and it's a profitable business. And good income can be generated by sewage farming. What are the methods of application of sewage? Sewage, which is rich with these elements, understand, instead of throwing it, definitely can be used for irrigation purposes. You can use it on the surface of the field. So that is called a surface irrigation methods, or you can go for subsoil irrigation method, or you can sprinkle it or the spray irrigation. So 3 methods of application of sewage are surface irrigation methods, the subsoil irrigation method, and spray irrigation method. Surface irrigation. This method is most suited in sloping area. Here parallel drains are constructed in the fields. All these drains are connected to a distributories drain with the help of regulating device, so that sewage may flow in the required drain. Here, when the sewage flows over the fields, large quantity is absorbed by the field. So it's nothing but, as the name says, it is applying on the field. Excess quantity reaches another drain. Another form of surface irrigation is flooding. Area to be irrigated is divided into various spots surrounded by dikes. Sewage is filled like small ponds in between the dikes. The depth of the dose varies from 3 to 5 centimeters. Just ಮಾಡೋದಕ್ಕಾಗಲ್ಲ. ಸೊ ಫ್ಲಡ್ಡಿಂಗ್ ಮಾಡೋ ನಾವು ಇರಿಗೇಷನ್ ಮಾಡ್ಬೋದು. ನೀರು ತುಂಬಿಸಿ ಮಾಡ್ತೀವಲ್ಲ, ಆ ಥರ ಸೀವೇಜ್ ತುಂಬಿಸಿ ಮಾಡೋ ಅಂಥದ್ದು. ಇಲ್ಲಿ ಒಂದು ಫಿಗರ್ ತೋರಿಸ್ತೇವೆ ನೋಡಿ. ಫ್ಲಡ್ಡಿಂಗ್ ಮಾಡಿದ್ದಾರೆ, ಸುತ್ತಮುತ್ತ ಬಂಡ್ ಹಾಕಿ ಡೈಕ್ ಮಾಡಿಕೊಂಡು ಅದರಲ್ಲಿ ನೀರು ತುಂಬಿದ್ದಾರೆ. ಅದರಿಂದ ಡೆಫಿನೆಟ್ಲಿ ಯು ಕ್ಯಾನ್ ಗ್ರೋ crops. Another method is basin method. In this method, big trees are planted in an isolated manner. Basins are formed around each tree. and these basins are filled with sewage. This method is suitable for fruit gardens. So basin ಮಾಡ್ದಂಗೆ ಮಾಡ್ಬಿಟ್ಟು ಅದರೊಳಗೆ ಸೀವೇಜ್ ತುಂಬ್ತಾರೆ, ಮರಗಳು ಬೆಳೆಸೋಕ್ಕೆ, ಫ್ರೂಟ್ ಗಾರ್ಡನ್ ಮಾಡೋದಕ್ಕೆ. So here we are applying sewage instead of throwing it. Ridge and furrow irrigation. In this method, sewage is supplied in furrows between crop rows. Sewage spreads laterally, irrigating the area between two furrows. The width of furrow vary from 120 to 150 centimeter and depth from 25 to 50 centimeter. The width of ridge varies 1 to 5 centimeter and length from 10 to 30 meters. The percolated effluent is collected in the underground drains, flows towards the natural drainage disposal. ಇಲ್ಲೇ ನೋಡಿ ರುಡ್ಜ್ ಅಂಡ್ ಫರೋ ಇದೆ, ಅದೇನು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದ್ದೀನಿ ಇಲ್ಲಿ ಫಿಗರಲ್ಲಿ ತೋರಿಸ್ತಾ ಇದ್ದೀವಿ. ಈ ಥರ ಮಾಡಿಕೊಂಡು ಸೀವೇಜ್ನ ಬಿಟ್ಬಿಟ್ಟು we can grow the crops as the sewage has got all the nutrients. ಸಿ ಇದೆಲ್ಲ ಸರ್ಫೇಸ್ ಇರಿಗೇಷನ್ ಏನು ಮೇಲೆ ನೋಡಿದ್ವಲ್ಲ ಹಿಂದೆ, ರಿಡ್ಜ್ ಅಂಡ್ ಫರೋ, ಬೇಸಿನ್ ಮೆಥಡಲ್ಲಿ ಪ್ಲಾಂಟ್ ಸುತ್ತಮ ಇದು ಮಾಡೋ ಅಂಥದ್ದು, ಫ್ಲಡ್ಡಿಂಗು, ದೀಸ್ ಆರ್ ಆಲ್ surface irrigation. You can go for subsurface irrigation also. Here, sewage is applied at the roots of the plants through the open jointed agricultural drain pipes. These pipes are laid about 1 meter below the ground level. The sewage rises ಕೆಳಗಡೆ ಇರುತ್ತೆ 1 meter ಕೆಳಗೆ. The sewage rises up due to capillary action and soil takes fewer loads, but this is an economical method. So subsurface irrigation method illa ant ಹೇಳಿದ್ರೆ what you can do is you can go for spray irrigation. ನೀರನ್ನ ಹೇಗೆ ಪಂಪ್ ಮಾಡ್ತೀವಿ ಆ ಥರ ಸೀವೇಜ್ನ effluent sewage is spread over the land through nozzle of pipe under pressure. If sufficient head available and the wastewater have no solid matter ಇರಬಾರ್ದು, no solid matter should be present in the one, otherwise it is going to choke up the nozzles. It can be sprayed under pressure, but it looks a very costly affair for this one. So spray irrigation. So this is a figure for subsurface irrigation. ನೋಡಿದ್ರಲ್ಲ 1 meter, as I explained, 1 meter below the ground level ಕೆಳಗಡೆ. So they have put the pipes. So they'll leave the sewage, and the sewage comes up due to the capillary action, and it is going to touch the roots. And this is what we discussed, spray irrigation. So here the water is not being sprayed, it is the sewage. So sewage farming is nothing but utilizing the sewage for growing up of crops. It may be 3 categories, that is surface irrigation or subsurface irrigation, or you can go for spray irrigation. These are the references: wastewater engineering, agrohealth publications, and sewage disposal and air pollution by Garg is used, and NPTEL sources have been used.